Hi my dear students, welcome back to our amazing YouTube channel of Brilliant Qatar. Hope you all are doing absolutely great. This is the 7th video lecture in our JEE Mantra series, and in this video lecture we will be revising matrices and determinants. First we'll go with matrices, then followed by determinants. Now coming to matrix, how do we define a matrix? Friends, any rectangular arrangement of given m into n numbers is called as a matrix. So each specific arrangement of m n numbers will be a specific matrix. And these numbers can be real or even complex numbers also, or real valued expressions or even complex valued expressions also. So any rectangular arrangement of given numbers, whether they can be real or complex or real valued or complex valued expression, is called as a matrix. Next, if a matrix has m rows and n columns, then order of the matrix, or we say type of the matrix, is called as m by n. We write it as m into n, but we read it as m by n. Clear? Now, in general, this is how a matrix which is having m rows and n columns looks like. First row, second row, third row, and so on. Mth row, first column, second column, third column. Now, in general, we write it as a matrix. This matrix can be written as matrix of elements Aij, matrix of elements Aij. Order m by n, if I give order m by n, then this I value of I, 1 less than or equals to I less than or equals to m, I takes from 1 to m, and j, if the order is m by n, number of columns will be n, so j will take from 1 to n. This is how in general a matrix in short form represented as. Now in general, matrices are denoted with capital letters, and the elements of a matrix are with small letters. In general it is. In general, let's say matrix A is equals to matrix A, B, C, D. Matrices are denoted with capital letters, elements are denoted with small letters. Next, types of matrices. First we start with row matrix. So if a matrix is having only one single row, then such matrix is called as row matrix. Column matrix. If a matrix has only one single column, then such matrix is called as column matrix. Example of row matrix. Let's say matrix 1, 4, 8 is a matrix which is having only one row, but how many columns? 3 columns. Whereas column matrix, matrix A is equals to A, B, C. This is having only one column but having 3 rows. So order of this matrix is 3 by 1. Order of this matrix is 3 by 1. Next, zero matrix. A matrix is said to be zero matrix if each and every element or each and every entry of that matrix is 0, then such matrix is said to be a zero matrix. In general, we denote zero matrix as O. Zero matrix as O. Order m by n, O m by n will always be equals to, that is, for all Aij is equals to 0. For all I and j. So for all I and j, if Aij is equals to 0, then such matrix is called as zero matrix, or we say null matrix. Next, square matrix. As earlier we have discussed, a matrix in which number of rows is equals to number of columns is called as square matrix. Next, diagonal matrix. Diagonal matrix means a matrix is said to be diagonal matrix. A square matrix is said to be diagonal only if all the non-diagonal elements should be 0. So a square matrix of order n is said to be diagonal matrix if Aij is equals to 0 for all I not equals to j. So if I is not equals to j, then all elements Aij will be non-diagonal elements. If I equals to j, then such elements will be diagonal elements. So if in any matrix, if all the non-diagonal elements are 0, then such matrix is called as diagonal matrix. Next, scalar matrix. In scalar matrix, even this is also a diagonal matrix, but all the diagonal elements will be same in this. Okay, all the diagonal elements will be same in this. Such matrix is called as scalar matrix. Now coming to identity matrix or unit matrix. It is also a scalar matrix, but here all the diagonal elements will be equals to 1. All the diagonal elements will be equals to 1. So in general, we denote identity matrix of order n as In. as In. So I2, that means the identity matrix of order 2, identity matrix of order 3. Next, upper triangular matrix, lower triangular matrix. A matrix is said to be upper triangular if all the elements lying below principal diagonal, below diagonal elements, if all the elements are 0, then such matrix is called as upper triangular matrix. And a matrix is said to be lower triangular matrix if all the elements which are lying above principal diagonal are 0, then such matrix is called as lower triangular matrix. Next, matrix multiplication by a scalar. If A is any matrix, see friends, if A is any matrix 1, 2, 3, 2, 7, 1, then scalar multiplication of a matrix. If this matrix is multiplied by a scalar, let's say some 2. Now 2A is nothing but we are going to multiply each and every entry, each and every element by this 2. So 2 1s are 2, 2 2s are 4, 2 3s are 6, 2 2s 4, 2 7s 14, 2 1s 2. So this is what scalar multiplication of a matrix mean. Next, nilpotent matrix. Friends, these are very important for JEE, very important. We have very good questions based on this. Nilpotent matrix, idempotent, involuntary and orthogonal. Now coming to first nilpotent matrix. A matrix, a square matrix of order, any order, is said to be nilpotent if A square is equals to O. If A square is equals to O, then A is said to be nilpotent of order 2. Clear? A is said to be nilpotent of order 2. Now if A square is not 0, then we check for higher powers, higher exponents. If A cube is 0, then A is said to be nilpotent of order 3. If A power 4 is 0, A is said to be nilpotent of order 4. So and so on. That is, if A power P is equals to 0, friends, the least value of P, the least integral value of P is called as order of the nilpotency. Clear? Next, idempotent. A square matrix capital A is said to be idempotent if A square is equals to A. Next, involuntary. If A square is equals to I, then such matrix is called as involuntary matrix. Next, last, orthogonal matrix, which is very important. Orthogonal. A square matrix capital A is said to be orthogonal matrix if A into A transpose is equals to A transpose into A is equals to I. Any square matrix. We'll discuss what is transpose, but before that, orthogonal means a square matrix capital A is said to be orthogonal if A into A transpose is equals to A transpose into A is equals to I. And moreover, important conditions regarding orthogonal matrix. If capital A is any orthogonal matrix, then its determinant will always be plus or minus 1. Next, and inverse of orthogonal matrix is equals to its transpose, friends. Inverse of orthogonal matrix is always equals to its transpose. A transpose is equals to A inverse. Next, equality of matrices. Two matrices are said to be equal if number 1, their order should be same. Number 2, all the corresponding elements should be same. So if these two satisfy, then we say two matrices are equal. Addition of two matrices. So two matrices, addition or even subtraction of two matrices. Two matrices are said to be compatible for addition or subtraction only when if they are having same order. First thing is they should have same order. Then how do we add or subtract elements means, how do we add or subtract matrices means, adding their corresponding elements. So A and B are now, A is a matrix of order 3 by 2. B is also a matrix of order 3 by 2. Then A plus B will also be a matrix of order 3 by 2. Then how do we get A plus B? Adding corresponding element. First row, first column element, first row, first column element. 1 minus 1, 0. Minus 1 plus 2, 1. 2 minus 2, 0. 3 minus 3, 0. 1 plus 5, 6. 0 plus 7, 7. That's how we get A plus B. Next, subtraction also same. Properties of addition and scalar multiplication. Number 1, friends, see, A any matrix, B any matrix of same order, then A plus B will also be of the same order. A plus B is equals to B plus A. Addition of two matrices is always commutative, is also associative also. A plus B of plus C is equals to A plus of B plus C. Null matrix or zero matrix is called as additive identity. Next, Additive inverse is for every matrix A, minus A is said to be additive inverse. Next, lambda of A plus B is lambda A plus lambda B, lambda into A is A into lambda. All these we discussed in scalar multiplication. Next, multiplication of two matrices, friends. How do we multiply two matrices? Capital A and capital B are said to be compatible for multiplication only when number of columns in A should be equals to number of rows in B. So that is, if I write m by n, A is having order m by n, then n number of columns in A, it should be equals to n number of rows in B. So this should be equals to some n by p. If B has order n by p, then A into B, we can multiply two matrices A and B. A and B will exist, and if this is equals to C, the resultant matrix will be having order m by p. Okay, I'll just give you one simple one. 1, 2, 3, 4 and B is equals to 2, 1. See now, this is a matrix of order 2 by 2, whereas B is a matrix of order 2 by 1. Now when you multiply A and B, can we multiply A and B? Yes, of course, because number of columns in A is equals to number of rows in B. Now, how do we multiply these two matrices? 1, 2, 3, 4, 2, 1. We can multiply row with the column. So 1 into 2, 2 plus 2 into 1, 2. 1 next 3 into 2, 6 plus 4 into 1. So we get 2 plus 2, 4, 10, and the resultant matrix is also having order 2 by 1, which is nothing but, see, if these two are same, the resultant order will be 2 by 1. That's how we get 2 by 1, and that is how we multiply two matrices. Next, matrix multiplication is not commutative, friends. That is, A into B may or may not be equals to BA. Okay, in general, AB not equals to BA. It is associative. AB of C, same order. It should be in the same order, friends. In the same order. AB of C is equals to A of BC. Next, IN is said to be identity matrix is multiplicative identity. Next, for every non-singular matrix, non-singular means determinant of a matrix. So if determinant is 0, it is singular matrix. If determinant is non-zero, then it is non-singular matrix. Now, for every non-singular matrix, that is det A not equals to 0, there exists a unique matrix B such that A into B is equals to B into A is equals to IN. That is, B is the inverse of A. Okay, so B is inverse of A, and we say multiplicative inverse. Lambda is any scalar. This is what scalar multiplication, and these two are A of B plus C is AB of AB plus AC, distributive. A plus B of C is AC plus BC, in the same order, friends, in the same order. A into C, AC, B into C, BC. Same order we have to write. Next, transpose of a matrix. So if a matrix is obtained by interchanging the rows and columns of the given matrix, then such matrix is called as transpose of the given matrix. So let's say A is any matrix of order 3 by 4 it is. Now its transpose, generally transpose is denoted as either A dash or A power T like. Okay, now see this, friends. When you transpose the given matrix, order will also be reversed. 3 by 4 becomes 4 by 3 now. Now first row becomes first column, second row becomes second column, third row becomes third column. Clear? Next, for any matrix A transpose whole transpose will be equals to A transpose whole transpose. The transpose of a transposed matrix is the given matrix itself. Lambda be any scalar, lambda A whole transpose is equals to lambda into A transpose. Lambda A whole transpose, you can just remove that lambda out, then lambda into A transpose. A plus B whole transpose is A transpose plus B transpose. This is next. For multiplication it will be reversed, that is A into B whole transpose will be equals to B transpose into A transpose, friends. Just A into B whole transpose is B transpose into A transpose, and this can be extended to any number of matrix multiplication. Suppose if I have A into B into C whole transpose, this is nothing as C transpose into B transpose into A transpose. Next, symmetric and skew symmetric matrix. In simple words, a square matrix A is said to be symmetric if A transpose is equals to A. That's it. And A square matrix capital A is said to be skew symmetric if A transpose is equals to minus A. Example of symmetric matrix. See, 1, 3, 3, 4. Now, if you first row 1, 3, A transpose is first row is 1, 3, second row is 3, 4. Now we got the same matrix. Such matrices are called as symmetric matrices. Skew symmetric matrix. For skew symmetric matrix, always the principal diagonal elements should always be 0. So 0, 0, minus 1, plus 1. Now what is A transpose ma? A transpose will be 0, minus 1, 1, 0. Now what is minus A? If you multiply with minus A, then we get 0, 1, minus 1, 0. So A transpose is equals to minus A. Such matrix is said to be skew symmetric matrix. Next, every square matrix can be expressed as the sum of symmetric and skew symmetric matrix. So when you add any matrix with its transpose, it will always be symmetric. This is symmetric matrix. And when you take the difference of any matrix with its transpose, you will be getting skew symmetric matrix. So every square matrix can be expressed as sum of symmetric and skew symmetric matrix. So this is regarding matrices, friends. Next, we'll go with determinants. Now in determinants, first, what do you mean by determinant? Matrix is arrangement. Matrix is arrangement. Determinant is a scalar. So if A is any square matrix and determinant is only for, determinant is a specific property, will be valid only for square matrices. Okay. Now determinants, if A is any square matrix, then determinant of that matrix is denoted as det A, friends. We read it as det A. Now in general, determinant of 1 by 1 matrix, let's say we have a matrix A is equals to some 2. Now for 1 by 1 matrix, determinant is the element itself. For 2 by 2 matrices, if A is equals to some 2, 1, 3, 4, determinant of 2 by 2 matrices is, we multiply principal diagonal elements 2 into 4, 8, minus we multiply these two non-diagonal elements, 3 ones are 3, so 8 minus 3, which is equals to 5. Determinant is a scalar. That means determinant of every square matrix is always a real number. It can be positive, it can be negative, it can be anything depending upon the entries. If the entries are real, it will be real. If the entries are complex, it will be complex. Please keep this. Next, 3 by 3 matrix. So if we have a 3 by 3 matrix, in general, 1, 2, 1, 0, 1, minus 1, 0, 0, 3. Now determinant of this matrix, we can expand by either any row or any column. If we expand by this first row, we take plus minus plus. This is initial stage of finding determinant. So plus 1 into determinant of this 1 into 3 minus 0 minus 2 times of 0 into 3 minus 0 into something plus 1 into 0 into 0, 0, 0. So then we get 3. Determinant of this 3 by 3 matrix is 3, friends. Okay. Now, next, another some basic terminologies of determinants: minors and cofactors. Minors and cofactors. Let me take a square matrix, capital A 3 by 3 matrix having elements A11, A12, A13, A21, A22, A23, A31, A32, A33. So this is a square matrix of order 3 by 3. Now see this, friends. For every element there will be a minor, corresponding minor and cofactor. First we will understand what is a minor. So for an element Aij, for every element Aij there will be corresponding minor. Now for A11, let's say A11, minor of an element Aij is denoted as Mij. Okay. So how do we get that minor? Now minor of A11, if I say minor of A11 is nothing but M11. Now how do we get this M11? For that we have to delete this ith row and jth column. So first row we have to delete, first column we have to delete. Then we will be getting a square matrix. Then you will be getting a square matrix. The determinant of that square matrix, that is determinant of A22, A23, A32, A33 is said to be its minor, friends. So minor of every element can be obtained by deleting that ith row and jth column. Will be getting a square matrix. The determinant of that square matrix is said to be its minor. Clear? Next, cofactor. Cofactor of Aij is denoted as Cij. Now how do we get Cij? Cij is equals to minus 1 whole power I plus j into Mij. So that means to get cofactor of that particular element we need minor. Minor multiplied with minus 1 whole power I plus j. Minus 1 whole power I plus j into Mij is said to be cofactor of that particular element. Now suppose if all the elements of a matrix, friends, if all the elements of a matrix are replaced by their corresponding cofactors. Let's say corresponding cofactor of A11 is C11, C12, C13, C21, C22, C23, C31, C32, C33. This is a matrix which is obtained by replacing the elements A11, A12 and these elements by their corresponding cofactors. This matrix is called as cofactor matrix of the given matrix. Given matrix is A, no? So cofactor matrix of A is said to be Ca. Ca means the elements of the matrix A are replaced by their corresponding cofactors. Then such matrix is called as cofactor matrix itself. Okay. Now this from here we define determinant, friends. Now how do we define determinant? Determinant of the matrix capital A, how do we get it? The sum of the product of the elements, of any row or column, by their corresponding cofactors of the same row or same column. The sum of the product of the elements of any row or column by their corresponding cofactors of the same row or same column is said to be determinant. So that means if we take first row elements, then we have to take first row cofactors. So det A is equals to A11 into C11 plus A12 into C12 plus A13 into C13, or second row elements with second row cofactors, third row elements with third row cofactors, first column elements with first column cofactors, second column elements with second column cofactors, third column elements with the third column cofactors. We get determinant of that square matrix. So see, now for a 3 by 3 matrix we can get determinant by how many ways? 6 ways, and all these 6 values will be equal because it is the determinant. Now, and one more thing, suppose if you are taking the sum of the product of the elements of any row or column by the corresponding cofactors of other row, by this corresponding cofactors of other row, then that value is said to be 0, friends. So that means if you take first row elements from this, instead of taking first row cofactors, if you take either second row or third row, then that sum is 0. That is A11 into C21 plus A12 into C22 plus A13 into C23 is equals to 0. First row elements with second row cofactors 0. Second row elements with first row cofactors 0. Okay. Third row elements with the second row cofactors will always be 0. So this is how we define determinant, and this is also important. Next, properties of determinant. In evaluating, in simplifying determinant, because in majority of the cases, now we know how to expand determinant. Sometimes the entries will be much difficult, entries will be much lengthy or higher values we get. In that case, direct expansion of determinant will lead us to time taking and much lengthy. So in all those cases, what we do, we use the properties of determinant for simplifying the entries only. So these properties will make the entries very simple, and then at one particular moment, if we can expand the determinant, then that we will be getting it in just 1 or 2 steps itself. Okay, now we have some 10 plus properties. First we'll go with property 1. Determinant of A is equals to determinant of A transpose. Though we interchange rows and columns, the determinant will be unaltered. This is the first property. Second property, if any 2 rows or 2 columns are interchanged, then the value of the determinant is changed in only sign, friends. See D1. In D2 we have interchanged R1 and R2 have been interchanged. So the second matrix, the second D2 is equals to, determinant of second matrix is D2 is equals to minus D1. D2 is equals to minus D1. Next, scalar multiplication of a matrix we have seen. Scalar multiplication by determinant. Lambda into determinant of A, we multiply this lambda with either any one row or one column. So this lambda will be multiplied with the elements of either first row or second row or third row or first column or second column or third column only. So now we have multiplied D. See, we have a matrix D. Determinant it is. Determinant. D is equals to determinant of this. And if you have multiplied some k times D, then that becomes, we are multiplying the k with either all the elements of first row or all the elements of second row or all the elements of third row or elements of first column or second column or third column. With only one particular row or column we have to multiply, ma. Whereas scalar multiplication of a matrix we have seen, there we multiply with all the elements. Okay, so this is the difference between matrix and determinant here. Next, determinant of AB is det A into det B. Determinant of, this is again important, determinant of some KA is equals to K power n into determinant of A, where n is the order of the given square matrix. Next, a skew symmetric matrix of odd order will be having always its determinant value 0. Next, if a determinant has all the elements 0 in any row or column, then the value of the determinant will be 0. Next, if a determinant has any 2 rows or 2 columns identical or even proportional, then the value of that determinant will be 0. Next, properties are, if each element of any row, this is simple. If each element of any row or column is expressed as a sum of 2 terms of the determinant, then even determinant can also be expressed as sum of 2 determinant. This determinant can also be expressed as sum of 2 determinants, where R2 and R3 remain same in both the determinants. Only R1 will be changed in first and second determinant. Next, the value of determinant is not altered by adding the elements of any row by multiplied with the corresponding elements of another row, that is row operations. If we are going to change the R1 tends to see R1 plus some 2 times R2. If we are going to do this particular operation, now what we are going to do, we are going to change the elements of R1 added with twice the elements of corresponding elements of R2. So R1 changes to R1 plus 2R2, there won't be any change in the value of the determinant. Or R1 changes to R1 minus 3R3, no change in the value of the determinant. Next, last property, the sum of the product of the elements of any row with corresponding cofactors of any other row is always 0. That is what we have discussed in the beginning. Some frequently used determinants I have gathered, friends, so that it will be easy for us to, in simplification time, this, if you remember these things, it will be helping us a lot. So this is a skew symmetric matrix of order 3, so hence it is 0. Now this we can just do some operations. C2 changes to C2 minus C1, C3 changes to C3 minus C1. then we can just simplify this. This becomes 0, this becomes 0. We can expand with only first row, first column element. This can also be done with the same. This, if you can make R1 changes to R1 plus R2 plus R3, then you get A plus B plus C common in first row. That A plus B plus C can be taken common. So that's how we can simplify it. We can simplify all of them by using properties, and just I urge you to remember them. Remember these 5 determinants. Next, multiplication of determinants. If we have 2 determinants, friends, let's say A, B, C, D and P into Q, R into S. One thing is we can expand the determinant and then multiply, or if you wish to multiply directly, you can multiply either row with row or row with column, the general method which we do in multiplication. So row with row means AP, row with row, no, AP plus BQ, AR plus BS, CP plus DCP plus DQ, CR plus DS. So this is how we expand the determinant, then we can get it. Suppose if you are going with the row column, so general way of doing by multiplication, AP plus BR, next AQ plus BS, CP plus DR, next CQ plus DS. So either you can use this or this to multiply 2 determinants. Next, adjoint of a matrix. From now the actual importance of determinant starts. Now what do we mean by adjoint? Just now we have seen in when we are finding the definition of determinant, we have taken a square matrix capital A. Let's say entries A11, A12, A13, A21, A22, A23 and A31, A32, A33. Now we already know corresponding cofactor matrix. Cofactor matrix, how do we get cofactor matrix? By replacing the elements with their corresponding cofactors. C11, C12, C13, C21, C22, C23, C31, C32, C33. Now, see friends, now the transpose of the cofactor matrix, transpose of the cofactor matrix is called as adjoint of the given matrix. That's it. Adjoint of given square matrix is nothing but transpose of the cofactor matrix. That's it. Transpose of the cofactor matrix is its adjoint. Okay. One most important relation with respect to adjoint is, friends, if you multiply A with adjoint A into adjoint A, or if we multiply adjoint A with A, these two are equal and this is equals to det A into I we get. A into adjoint A is always equals to adjoint A into A is equals to det A into I, which is one of the most important relation for everything now. From now, this is everything. Next, inverse of a matrix. Inverse. A square matrix capital A, okay, if it is non-singular, that is det A is non-zero, if det A is non-zero, then a capital A matrix A is said to be invertible. So if it is non-zero, then for sure there exists a matrix B such that A into B is equals to B into A is equals to I, friends, and this B is called as inverse of the given matrix. This B is called as inverse of the given matrix. Now just now we have seen an important relation in terms of adjoint. So adjoint A into adjoint A is equals to adjoint A into A is equals to det A into I. No, we do one thing, we'll divide with the determinant. When we divide with the determinant, what do we get? We get A into adjoint A divided by det A is equals to adjoint A divided by det A into A is equals to I. Just compare this with this, friends. So if we compare this with this, in place of B we have, so A inverse is equals to, inverse of the given matrix is equals to adjoint A divided by det A. That is why det A should be non-zero. Okay, why only inverse exists for non-singular matrix? Because A inverse is adjoint A by det A. If det A is non-zero, then only inverse exists. Okay, so now A inverse is equals to adjoint A by det A. We'll see some properties of inverse and adjoint, friends. Now A inverse will always be singular, non-singular. First condition is the necessary and sufficient conditions for existence of inverse is it should be non-singular. If it is diagonal matrix, then A inverse is just the reciprocal of diagonals. A inverse whole transpose is equals to A transpose whole inverse. A inverse whole inverse is A itself. Let K be any non-zero scalar and A be non-singular matrix, then Ka whole inverse is 1 by K into A inverse. Determinant of A inverse is 1 by det A. Next, 8th one, friends. Let A be non-singular matrix and AB is equals to AC implies B is equals to C. See, if A is non-singular only, then only this is going to be true. Why? Because if AB is equals to AC, if A is non-singular, then we multiply inverse of A both sides. A inverse into A is I into B is equals to I into C. IB is equals to B. So B is equals to C. So this is true only when A is non-singular. Only if the condition given that A is non-singular, then only we can say that B equals to C. Okay, so in general, friends, AB whole inverse is B inverse into A inverse, same like transpose. So in general, if AB is equals to 0, does not imply either A0 or B0. If A is non-singular and AB 0, then in that case B is 0. And similarly, if B is non-singular and AB 0, in that case A is 0. Therefore, if AB is 0, either both are singular matrices, or one of them is a zero matrix. It can be true that AB is equals to 0. First, both are singular or one of them is a zero matrix. Need not that both A and B should be 0. Properties of adjoint. Next. So determinant of adjoint A is det A whole power and det A whole raised to n minus 1. Here n is the order of the given square matrix. Adjoint of adjoint A is det A whole power n minus 2 into A. Determinant of adjoint A is det A whole power n minus 1 whole square, friends. Here we have T adjoint of adjoint. 2 times we have adjoint, so n minus 1 whole square. If we have 3 times adjoint of adjoint, then n minus 1 whole cube. Det A whole raised to n minus 1 whole cube. So that can be expanded. Adjoint of ABC, reverse. Adjoint C into adjoint B into adjoint A. Adjoint of Ka is K power n minus 1 into adjoint A. For Kb, n is scalar and n is the order of the given matrix. Adjoint of A transpose is adjoint A whole transpose. Next, characteristic equation of a given matrix. So for every square matrix, friends, there exists one characteristic equation. So how do we get that characteristic equation? So for a square matrix, what we do? We take A minus xi, determinant of A minus xi, we equate it to 0. To get the characteristic equation of the matrix A, then what we do? We take the determinant of A minus xi and we equate it to 0. We expand the determinant and we get the characteristic equation of that matrix. So for time being, I'll just take a simple 2 by 2 matrix. Let's say A is equals to some 1, 2, 3, 4, friends. Okay. Now what is A minus xi? What is xi? I is 1, 0, 0, 1. No. Now xi means x0, 0x. So A minus xi means 1 minus x, 2, 3, 4 minus x. Determinant of A minus xi, we equate it to 0. So that is determinant of 1 minus x, 2, 3, 4 minus x equated to 0. Now 1 minus x into 4 minus x minus 3 to the 6 is equals to 0. So if we simplify this, friends, 1 4 4 minus x minus 4x 1 into 4 minus x square 1 minus 4 1 into 4 4 1 into minus x minus x into 4 minus 4x plus x square minus 6 is equals to 0. So finally what we get? X square minus x minus 5x, 4 minus x minus 2 is equals to 0. Now if we replace x with a, then we get a square minus 5 times of a minus 2i. Why? To balance the equation. To balance, because it is a matrix equation, no? Characteristic equation of matrix. So 2 into 1, like 2 into I is equals to 0, is said to be the characteristic equation of the given matrix. Is said to be the characteristic equation of the given matrix. Okay. Next we'll go with the most important and the last part of determinants, that is solution of linear equations. Solution of system of linear equations. System of linear equations can be homogeneous and non-homogeneous. First we will go with homogeneous. So I'm directly going with the 3 by 3 matrix, friends. Whether it is 3 by 3 or 2 by 2, the approach is same. First, let me take a system of linear equations. A1x plus b1y plus c1z is equals to some d1. A2x plus b2y plus c2z is equals to some d2. A3x plus b3y plus c3z is equals to d3. Be the three system of linear equations. A system of linear equations. Solving system means you have to find the value of x, y, z. First what we do for solving by using matrix inversion method. First we'll solve by using matrix inversion method. In matrix inversion method, what we do? First we'll take 3 matrices A, X and B. A, X and B. A is called as coefficient matrix, X is variable matrix and B is constant matrix. So if you take A as coefficients A1, B1, C1, A2, B2, C2, A3, B3, C3. This is what we say coefficient matrix, order 3 by 3. And X is variable matrix, a column matrix we take X, Y, Z. And B is constant matrix D1, D2, D3. Now these 3 are related with the equation AX is equals to B, friends. Clearly when you multiply this with this, then only you will be getting A1x plus B1y plus C1z is equals to B means is equals to D1. That's how they are related. Okay. Now how we are going to solve by using matrix method, matrix inversion method. First, now we have the equation AX is equals to B, multiply with adjoint A both sides, adjoint A into AX is equals to adjoint A into B. We know adjoint A into A is det A into I. So det A into I into X is det A only. Now det A into X is equals to adjoint A divided by B. Clear? So we have got X is equals to adjoint A divided by det A into B. Clear? That means X is equals to A inverse into B. This is only when det A non-zero. This is only when det A non-zero. Now, so the solution, we have 2 cases, friends. Number 1, case 1. If det A is non-zero, if det A is not equals to 0, if det A is not equals to 0, then directly we get X is equals to A inverse of into B. Then from here we will be getting the values of X, Y and Z. Okay. So that means system is consistent. System is consistent and has unique solution. And has unique solution. This is regarding when det A non-zero. Now case 2, friends. If det A is 0, in this we'll split it into 2 cases. Number 1, if det A is 0, a right hand side part, that is adjoint A into B 0 one case, or adjoint A into B non-zero other case. If adjoint A into B is 0, 0 is equals to 0. That means whatever the values of X, Y, Z will satisfy. So in this case we say system is consistent again and has infinitely many solutions. Infinitely many solutions. Infinitely many solutions. Whereas if adjoint A into B not 0, see friends, now already det A 0, 0 into x 0 is equals to non-zero. Will this going to be true for any x, y, z? No. So in this case we say system is inconsistent. Inconsistent, or we say no solution. Unique solution, infinitely many solutions. Okay, so this is regarding solving system of linear equations by using matrix method. Suppose if we go with Cramer's method, then in that case what we do, we have three system of linear equations, no? System of linear equations, that is a1x plus b1y plus c1z is equals to d1, a2x plus b2y plus c2z is equals to d2, a3x b3y plus c3z is equals to d3. We consider three determinants, friends. We consider three determinants. Say d1, d2. We consider four determinants: capital D, d1, d2, d3. What is the determinant of the coefficient matrix? A, B, C, that is a1, b1, c1, a2, b2, c2, a3, b3, c3. This is D. Now d1 means we'll replace a1, a2, a3 by d1, d2, d3. So d1, d2, d3. Remaining two columns same: b1, b2, b3, c1, c2, c3. And D2 is obtained by replacing B1, B2, B3 with D1, D2, D3. So first column same: A1, A2, A3. Now D1, D2, D3, C1, C2, C3. This is determinant of D2. Next D3 is A1, A2, A3, B1, B2, B3. In place of C1, C2, C3 we replace D1, D2, D3. D1, D2, D3. Now, once we get x is equals to, the solution is x is equals to d1 by d, y is equals to d2 by d, z is equals to d3 by d. Okay. Now in this case, again we are having two cases, friends. Number one, suppose if D is equals to, that is determinant capital D is non-zero. If D is non-zero, then you get for sure x is equals to d1 by d, y d2 by d. So system is consistent and has unique solution. System is consistent and has unique solution. Unique solution. Case 2. If capital D is 0, in this case, again we split it into two cases, friends. Number one, in that all D1, D2, D3, if all three are 0, D0, D1, 0. In general, see, how do we get is D into x is equals to D1 before we dividing. Now D0, D1, 0. That means x can be any number, y can be any number, z can be any number. So in this case, what we say, system is consistent. System is consistent and has infinitely many solutions. Infinitely many solutions. Whereas if at least one of D1, D2, D3 is non-zero, friends. If at least one of them is non-zero, then we say system is inconsistent. System is inconsistent. That means no solution. no solution. Okay, so this is regarding what? Non-homogeneous. Suppose in case of homogeneous, what happens? Homogeneous equations means a1x plus b1y plus c1z is equals to 0. Homogeneous system it is. a2x plus b2y plus c2z is equals to 0. a3x plus b3y plus c3z is equals to 0. This is homogeneous system. Now solving homogeneous system is nothing but, see friends, already we know what is capital A, X and B. Now B is clearly a zero matrix. B is clearly a zero matrix. Okay, so we know Ax is equals to B and X is equals to A inverse into B. Now already if B is 0, we know. If B is 0, now in this case, number 1, if det A is non-zero friends, if det A is non-zero, non-zero means A inverse exists. A inverse into 0, you get 0, 0, 0. 0 matrix. So that means X equals to 0, Y equals to Z is equals to 0 is the unique solution we get. Unique solution, and this solution is called as unique solution. System is consistent, and this solution we have a special name called trivial solution friends. Trivial solution. Suppose second case, if det A is 0 man, if det A is 0, if det A is 0, in that case what we do, in that case in general what we have actually, in general what we have, adjoint A into A is equals to det A into A is equals to adjoint A into B. If det A is non-zero, if det A is 0, generally we don't take det A to the other side. Now in that case what happens? B is already 0, no? So 0 into adjoint A is 0, det A is also 0, 0 into X will also be 0. So for any XYZ it is true. So that means friends, that means system is consistent. Yes, system is consistent and has infinitely many solutions. Infinitely many solutions. And this case we say both trivial and non-trivial solutions we get. Non-trivial solutions we get. Non-trivial solutions. Okay, non-trivial means except 0, 0, 0 friends. Okay, trivial solution means 0, x0, y0, z0 is trivial solution. Non-trivial means apart from except 0, 0, 0, all the remaining solutions are called non-trivial solutions. Okay, now in the same way we can get it in terms of Cramer's method also. Now coming to Cramer's method, same again two cases. We have capital D, D1, D2, D3, no? Now anyhow, if this is 0, that means D1 is equals to D2 is equals to D3 is equals to all of them 0 only, no? Okay, so we'll split it into two cases ma. Det A is non-zero, det A is 0. If det A is 0, we get unique solution. See, when all homogeneous system is always consistent. Homogeneous system is consistent. Now the thing is whether it has unique solution or infinitely many solutions, that we have to understand. So if D is non-zero, it has unique solution. And what is that unique solution? That is x0, y0, z0, and this solution is called as trivial solution. And if D is 0 friends, then it has infinitely many solutions. Infinitely many solutions. And in that case what we say, both trivial and non-trivial solutions we get. Non-trivial solutions we get. Okay, so this portion is very important, solving system of linear equations. With that we are done with complete matrices and determinants. Okay, friends, see you in the next session. All the very best for your exams. Take care everyone. Bye. God bless you all.